Hello, everybody, and welcome to Dot to Dot. Today, I'm going to talk about how we complete the island side of the Zena Halper map, or the Oak Island document, is whatever you want to call it. This is something that we've been working on for quite a long time, and it's really just come to light recently, and I want to share it with you because one of the big questions is uh, if you've seen the geometry on the quadrant side, which is this side here, how do you translate it over to the island side without using Google Earth? Well, it's all geometry. The document that you see before you is a geometric progression, and the geometry comes from knowing what geometry to apply for one thing, and then also the clues, the little pictorials, and the little uh, mistakes in spelling and things like that all give us guides and clues on what to do, and it's highly interpretive. But when you do the geometry, it just becomes beyond coincidence. So today I'm going to show you how that you transfer from the quad side of the geometry from the quad side of the map to the island side without overlaying on Google Earth. I know I'm using Google Earth, but Google Earth is the only application that I have to draw lines and measure. So first thing we're going to start off is we're going to orient this to north south because this is one of the reasons why this quadrant is situated in this way. It's for uh, the ability to project what we're going to do onto the island side of the document. So the first thing is I'm going to show you just the quadrant side geometry so you can understand what we're doing here. Now, I won't get into how all this geometry is, uh, you know, you can pretty much see how it's formulated through all the different clues, and these are in my past videos. But uh, to make this so short as possible, not to get all into this again, is the dimension of this line, which is 5978, when you divide it by the 1347 or 1444, you get a ratio. And this ratio is to determine basically this dimension up here, which is 1775 on this scale. And if you divide it by that 4.14, you get 429 feet. And if you remember, this is the distance from here to here, or from cone D to the headstone. And that's what this actually represents, is cone D on Nolan's Cross to the headstone. And then it's doubled, giving us a total diameter of 858 feet. So remember that. This is the diameter of 858 feet. Another thing, too, is this is to be understood to be an east-west line by this, the interpretation, a little v wanders west, and you see the wandering here. So this line, which comes from this little v here, goes through the center of the quadrant, and it is going east to west. So this orientation of this will be east to west, making this line right here going at 60 degrees true to north. So one of the things that is important to understand too is, and Olivier recognized this when we first started working at this little symbol right here reminded him of a geometric theorem called the intercept theorem, developed by a Greek mathematician called Thales, Thales. And this is a geometric theorem. This is here, I'll show you a little picture of it. This is the theorem we're going to talk about where we have the a point, the intercept point, and two lines that come and intersect at this point will have triangles that are proportional one to another. This little triangle is proportional to the larger triangle. So this is the theorem we're going to use. I hope I haven't lost you yet. This is important because we want to be able to establish that this document has the geometry to completely show Nolan's cross, which is basically its function. So let's see. We start off with we're going to put this right here, and this is basically what we're working with on this theorem. We're going to drop the north line down through the center, and if you notice, it really doesn't touch anything until we go past, because we're going to project onto the island. It doesn't touch anything until it comes down to this little lightning bolt and the dot right here. So by logic, we assume that this is going to be where the intercept point is going to be. So what we do is, just like in the theorem, we go from the dots up here at the diameter, and we project those down. And it's very interesting, the clues that I believe this author gives us to show that you're in the right direction. Notice this little dot right here on the thing. Notice how it goes right along the side of that. And we have we'll put the dot at the center here. We have a dot here. And also we have a dot at where it crosses the island border right here. So just these little clues, whether you believe them or not, I use them as guides to set up this geometry. So let's see. The next thing is we're going to draw a line. Since this is the only place really where we have any guides or clues, notice how it's going through the center of the triangle. We're going to draw a line that goes through the other point of the triangle. And notice how it hits this S at the top, and it hits the sort of tangent on this dot right here, which we call Ian's head. And we go across to the other line. Now, these angles, according to the theorem, need to be parallel, and they are set parallel to one another. So these are parallel lines, and I believe it's 105 degrees to 825, 180. So I set those to that angle. And we're going to put a center in the dot right over that S, and that is actually the center of the circle. So this S gives us a really good clue that that's where that center of that circle is. And when we do that, get these 2 points on here, we find out that this dimension of this line is 858 feet. So remember, the scale up here, this was 1,775 feet according to our measurements on how we're measuring this. And this now is 858 feet, which is basically the factor 1775 divided by 4.14, which gave us 858. So we have the proper scaling of this dimension according to the geometry on the quadrant side. Another interesting thing about this is that if we look at this little lightning bolt clue, it points to the center where this line crosses the north-south line. So we put a dot there, and the only thing I can think of to do is to draw a circle around that. So I did that as a center, and this circle is equal This circle is has a circumference of 296 feet, and this one has the measurements of 269 4 feet. They're 1 foot off each side, so they're pretty close to one another. But when you get these two circles, equal circles together, we get an intersection point at this line right here. And if you remember, we're going to put in an angle of 60 degrees through that line. And when we do that, we get the angle such as this. This is 60 degrees to the north-south line. And this actually matches the angle of Nolan's Cross, the axis of Nolan's Cross. So we have, this is actually island scale. So this is actually the island itself overlaid on Google Earth. But this theorem works at any proportion. You'll still get the same ratio, which is 4.14 of the quadrant dimension. So any dimension that you get down here from doing this, if you multiply it by 1.14, you will get the same dimension as the quadrant here. And whatever scale this is set to, it's 1444 can be determined, and this is what is basically the distance between the north anchor and cone E on Nolan's Cross. So this is interesting. Another aspect about this is the distance right here of from the set line, from the set point to here, is the same distance that's going to be measured from the point on Frog Island to the set point on this island. And this is determined pretty much by the little triangle down here where we put a point right here and find 3 times the island scale. And let's see. So we have 3 times the island scale. We get this point. And this line right here is the same measurement as the line that is up here. It's the same distance. This line and this line are the same. So he makes it very convenient, the author of this, to make the distance easy to ensure that you'll get the proper distance. Another thing is when you know that that is true, you can take your scale distance of 1444 and subtract that from the total distance, and you get this point right here, which is the 429 point, and that is the point on the scale right here, or on the quad side. That is this point right here. And so we know that Nolan's Cross will be at a 20-degree angle to that, and that's what we have here, the 20-degree angle for Nolan's Cross. But most importantly is we can go from this point, and if we work it backwards, we can find cone D. And we can find cone D by taking this point and drawing a circle that is equivalent to 429, which in this case it is 429. And we take that distance, 429, we find the headstone, and then if we double it again, we get cone D. So we get Nolan's Cross. Let's clean this up a little. So we can get Nolan's Cross and all the other cone E if we apply from the headstone, the 1444 measurement. You get cone E, cone D. And then interesting from this little dot right here, if we go parallel to the set point, or I'm sorry, to Lahomp, which I haven't really explained how that comes into play, but we get cone B, and perpendicular to that, we get the Nolans Cross here. Lahomp is found by the intersection of 1,444 feet from the set point that intersects this circle here, the 429 circle, but also the east-west line. And the east-west line is found by the fish again. And I remember I showed you how the fish gave us the set point. But if we go from that little thing right here, tangent to the eye, and it's funny because this all has to do with eyes. So we come down from the eye and we'll go through the dots of the eyes here. And here's another eye. If we follow this up, this came from this eye in the basin, and this big dot right here that's off the center, very bisected, the S here. All these clues are guides. And so this came into play, and when these things intersect, we have this where the boat is not supposed to go. We have this little clue here that shows us to look on this side of the eye. So, and then also this little tick that comes down, which I believe to mean it's going to go perpendicular to the north-south line. Another thing is the on the other side of the eye, if we go down, we hit some more eyes, the eye in Pierre and the eye in triangle, get basically a tangent taken off those dots. And we come down, and this is actually a 45-degree angle, which if you know 45 will give you a 90-degree angle, which is where these intersect. And this is the, notice it's tangent with this big 429 circle. So this is where the east-west line comes, and then you get Lahomp. And the other thing about where the boat is not supposed to go, let me put the north lines in. If we drop north lines from each of these points, I don't have that one here, I'm sorry. But if we drop north-south lines, and even from the boat right here, when we go off the center of the boat, we come down, and this hits the where it hits the shoreline. If you take a angle and go through where it hits the shoreline of the north-south, you end up at cone A. And the other thing is too, is with the boat, that's where you're supposed to go with the boat on this side of the island, because this is where the stones on Round Island are, where you can have a landmark, an actual landmark that gives you the sighting for this east-west line that goes through the middle of the island pretty much. And this is where Lahomp will end up. All this geometry on this island map is to give you a rough estimate, I think, of Nolan's Cross and the functionality of Nolan's Cross. So when you do get on the island, you'll have other things. You'll have Nolan's Cross for one thing, but you'll also have the five stone piles and the rocks, which are basically not there anymore. But you did have the 5 stone piles and the rocks that were up in this section of the island that have a direct connection to Nolan's Cross. It also has a connection to the set point. I can put that up, I think. But the Nolan stone piles were on the island, and they all have a connection, as you can see, to the set point and cone D, and also to the 429 extension and cone A. So this is how Nolan's Cross is so important to know, and it's not present on this document. And the reason is because that's what you're supposed to find. That's the nature of this document, to show you where Nolan's Cross is. So those are the things I have to show you. It's getting close to the Oak Island season, Curse of Oak Island. I'll be doing more videos pretty much as that's coming along, but this information is pretty intense. I was sort of skeptical on whether to present it to you or not, because you really have to get deep into it. But I'm telling you, there is a mathematical way to take the information from the quad side and project it onto this little map to give you an idea of where Nolan's Cross is, which is the main function of this document. Thanks for watching. Like and subscribe, and I'll talk to you later.